Okay, lecture 16. So today we will just study how can we use this device simulator, G device. So if you are familiar with this tool, then maybe that is quite boring, but to some of you, especially from undergraduate course, this tool is not open to you. So it may be a little bit challenging because we have to finish our tutorial within one lecture hour. So let me just try to cover them all without missing any important points. So anyway, let's talk 16. So previously we had the chance to generate a device structure. It was a quite a simple PN junction, but without relying on the Ångström-Craft code. So we were able to make a simple one. So it just assumed a certain simulation domain and assigned a certain region, actually multiple regions, and also define doping density and contact. So although the structure was quite simple, so just it was divided by just half to half for p-type. This is a p-type region and this is an n-type region. Actually you can do it in more complex way. As much as I understand, the only restriction on this shape is it should be a cuboid. So we cannot make such kind of a very smooth shape in here, but if that is just made like a small subset of cubes or cuboids, so then it is completely okay to have any kind of device structure. So although it is not as powerful as Ångström-Craft we have studied up to now, but at least we can make the final structure. Ångström-Craft is good for just to have a look at the progress of our structure, starting from one shape. After doing certain process job, then it is changed. So A is changed to A prime, and it will go to A double prime, and it will evolve and evolve. And this code G device, its mem maker routine is not suitable for tracing this change. But eventually we will have final device structure, and if we just wanted to describe this final device structure, then it is okay to just use this mem maker capability. So anyway, I will assume that you have already generated your device of interest as the final structure. Starting from that one, today we will just calculate two different things. What is equilibrium state of this final structure, and what is IV characteristics of that structure. These are usually taught in multiple lectures, but this course is not for introducing G device only, so I have to in hurry. Okay, so let me just go to quickly to the main topic. But at least I have to say this one. This is important to understand the behavior of our code. Carrier density at equilibrium should be calculated. So equilibrium means that in our sense, we do not assume, for example, the equilibrium in sense of a physics course. So we do not assume zero temperature. Instead, we assume certain temperature, typically 300 Kelvin or higher, lower, it's okay. But anyway, we assume that our device is surrounded by certain heat bath, so it is place that as a certain temperature, and this temperature is enforced to our device. So that is our basic assumption. In this case, if our system is in equilibrium, thermal equilibrium with a certain heat bath, then at equilibrium, our electron distribution function should follow well-known Fermi-Dirac distribution. So here T is corresponding to the temperature of our system. So also here we have E, that is the energy of a state, and here we have a Fermi level, and this is the reference level. For up to this level, electrons are more or less filled, and above this level we have almost no chance to fill these energy levels. Simply speaking, if we have EF, and if we have a certain state and another state here, then what is the probability to fill this state? Then there is almost no chance for us to fill this one. And if we have a certain state whose energy level, of course, this is the vertical axis, in this case energy, and if we have a quite a low energy state compared with the Fermi level, then it is more or less fully filled. And only above a certain energy level, around Fermi level, just a few kBT and a few kBT, we have deviation from these two extreme values, 0 and 1. Here we have a smooth transition from 1 to 0. So anyway, this is the result of thermal equilibrium. We can assume Fermi-Dirac distribution because electrons are from fermion, so we can assume this one. And another factor we have to consider is density of state. But in this case, usually we assume density of state follows square root of electron energy measured from its conduction band minimum. So if you have a look at this form, density of state follows square root of energy, it says that we are currently assuming three-dimensional K space. So that is assumed in this case. Silicon, we have three directions for our electrons can move. So this is quite obvious. We have a three-dimensional bulk system. However, if we consider two-dimensional material, monolayer two-dimensional materials, then this is no longer the case. We have to consider two-dimensional K space, or even if we have a carbon chain, then we have to consider one-dimensional K space. In these cases, actually this assumption, density of state follows square root of energy, that does not hold any longer. However, in our usual device simulator, still three-dimensional K space is assumed, and if we wanted to expand it to more recent research interest to the material, then we have to consider this generalized density of state. Density of state is just an indicator of its dimensionality. If it follows this kind of behavior, then this is corresponding to 3D K space. And if we have 2D material, then more or less density of state does not change according to this energy level. So it is like just step function of E minus EC. Beyond conduction band level, the density of state is more or less constant. So, well, that is another story. But right now, we will just concentrate on three-dimensional K space because silicon has really three-dimensional characteristic. So we can use this expression. So let's just put these two expressions into this integral expression for electrons, starting from the conduction band minimum energy up to infinitely high energy. So we have to make an integration between integration of a product between density of state and distribution function. So you have seen this kind of discussion in several times. Then if we perform that one properly, then we can arrive at this kind of expression. So here, of course, I made some approximations. One is here, although we have to consider Fermi-Dirac distribution, but already I have made this kind of expression approximation called as Maxwell-Boltzmann distribution. So here I assume that E minus EF is much higher than summer temperature. So since this argument is much larger than 1, so compared with this just number 1 and exponential of certain argument higher than 1, this one is dominating. So we can clearly neglect this number 1 compared with the exponential term. So that's the reason why we can have just minus of this expression. So this is quite a much well-known expression under the assumption of Maxwell-Boltzmann statistics, and this is quite acceptable for many cases. Of course, I'm not saying that this is really true, but this is quite much used, and we will rely on this expression. So here we have NC, and this is called as effective density of state of a conduction band. Of course, if we have a balance band, then we have to say this way. So effective density of a state of a balance band, but we have a conduction band here. Now we have this number. A density of state is actually density of state, energetic density of state. So usually when we say density of state, it is number per EV energy level. So that is usual dimension of density of state. But when we say effective density of state, it is no longer like this. Of course, sorry about that. I have to, of course, have this volume dimension here. So this is the usual dimension of density of state. But when we say effective density of state, we already perform this kind of energy integration. So energy dimension is gone. So simply speaking, NC, although it is called as effective density of state, but it is not energetic density. It is just number of states per given volume. So this is nothing but just volume density. We have seen this kind of a quantity several times, like intrinsic carrier density or electron density, hole density. They share the same dimension here. So anyway, the good news for this kind of study is now we can express our electron density simply a function of this one, EC minus EF, that really determines the electron density. So that is a really good one, because let me just emphasize its significance here. So the equation or the physical rule we have to consider inside the semiconductor device is Gauss law. We must consider electric field, and Gauss law just says that what is the physical origin of this electric field. Why do we have an electric field? The answer is, since we have a net charge density, so since there is a charge imbalance inside our system, therefore we have an electric field. That is meaning of our Gauss law. You can write down that here. So this is corresponding to so-called displacement vector, and here we have a net charge density. It simply says that this one, net charge density is the source of displacement vector. And since this displacement vector and electric field are quite much related within simple media, so in this case, so we can say that, okay, net charge density generate electric field. That is the Gauss law. We must satisfy this Gauss law everywhere, because this is a part of Maxwell equations. So now let me apply this expression to our specific case of semiconductor devices. So within semiconductor devices, we can think about how can we have this net charge density. If we are considering different systems, actually we can have, or we may have, different expressions for net charge density. For example, in many cases, in some cases, we consider sensor system. So there is a certain sensor system, and it is filled with water. And in that case, we can have many ions inside this water. And then if we have, for example, positive ion, then that can contribute to also this kind of net charge density. So in general, there are many different ways to have a net charge density, but since we are talking about solid state semiconductor device, so there is no like positive ion freely moving inside our system. All of our ions are just tied to the crystal structure. It cannot move. So we can say that although we can consider certain ionic charge from dopant, however, they should be regarded as just a fixed one. They don't move. And what are moving charges? Here we have two possible ways of moving charges here. This is hole density, and this is electron density. Yes, electrons and holes can move, so they are mobile charges. Of course, if we consider further, then we can think about other different contributions to this net charge density. For example, if there is a certain state which is in between conduction band level and valence band level, and that is highly localized, and in between this forbidden region, then usually we call it as a trap. And if we have a trap here, then that does not contribute to any kind of electronic conduction, because this is a real space and their position is highly confined, localized. They do not move. However, if a certain electron can have sufficient energy escaping from this trap density, then it can convert into the conduction band electron, and it can contribute to the electronic conduction. So if we have such a kind of a state and trapped electron, then of course we have to consider the contribution from this physical mechanism. So I'm saying that there are many other different capabilities, possibilities to have a net charge density. However, we will just consider these simple cases: two mobile carriers, electrons and holes, and fixed dopant density. in this case, then what is difficult one and what is relatively easy one? So we treat this doping density as an easier one under the assumption of fully ionized dopants. So, for example, if we have arsenic contents 10 to the 19 per cubic centimeter, let's say that the arsenic content is 10 to the 19, then it contributes to us positively charged arsenic atom cores whose density, volume density is also 10 to the 19 per cubic centimeter. That is our assumption. Why we can assume this kind of a full ionization is because arsenic levels are quite close to the conduction band level, and we have a sufficiently high temperature. So since energy, thermal energy is so high compared with or comparable to the energy difference between these two, so we can assume that almost all of our arsenic impurities are ionized, means that contributing their electrons to the conduction band and becomes almost empty. That can be the fully ionized situation. However, if we consider lower temperature, not like 300 Kelvin, for example, 77 Kelvin, or even nowadays much lower temperature, then what will happen? There is no guarantee that these kind of ions or impurities are fully ionized. So we have to consider ionization efficiency for these dopants, but also we will not talk about this advanced topic because we are currently talking about 300 Kelvin room temperature situation. So anyway, if we accept this kind of limitation of our discussion, then now we can say that doping density or so contribution from ionized dopant is more or less given as a function of a position only. And now we have hole density and electron density. Then how can we calculate these two quantities? That is our central question, and the answer is already given here. Now electron density can be obtained as energetic difference between conduction band minimum and Fermi level. And also we can answer in the same way. If we consider hole density, then energetic difference between valence band maximum and Fermi level, that really determines our hole density. So now we have two quantities. In order to consider electric field, then we have to introduce a certain kind of a quantity called as electrostatic potential. So they have this kind of relation. Electric field is given as gradient of this quantity called as electrostatic potential. Yes, so you can see it here. And also, we have to understand what is hole density and what is electron density, but we have seen that actually this is given as valence band maximum minus EF. That determines hole density, and also EC minus EF, that determines electron density. So combining them all, we must find out a closed solution of this Gauss law. So then maybe you can ask me this question. Oh, we have several of you unknown variables seemingly, then how can we solve it? So please have a look at this one. What is unknown? Yes, we must understand what is electrostatic potential, and we must understand what is valence band maximum, and we must understand what is a Fermi level and what is also EC. fortunately, all of them can be just eliminated, and we can have just only one thing. So electrostatic potential. So for that purpose, we must express our EC and EV and EF in terms of this electrostatic potential. I will quickly show you how can you do that. The simplest one is this one, Fermi level. So in the case of Fermi level, we just set it as 0 EV. So this becomes just a reference of our simulation. So that's the reason why we can clearly neglect this EF from our discussion. Reference. So at equilibrium, we may define the Fermi level globally, and that becomes 0 EV. So that is one thing we have. Now we have to eliminate this EC and EV, but there is also quite a good way to do that. So EC, so let me just show it to you. EC equal to EC minus EI plus EI. Here EI is intrinsic Fermi level. So I just made a minus EI and positive EI. So this is just identity. Nothing happens. But important observation is this EC minus EI. The distance between conduction band minimum and intrinsic Fermi level, this is material constant. So once we have silicon's EC minus EI is given, then only remaining quantity is now EI. So let me just repeat it once again. EV minus EI. You can do it. Sorry about that. So if we have EV, then it can be expressed as EV minus EI plus EI. And the difference between intrinsic Fermi level and balance band maximum, that is also given as a material property. So you know that in this case, since silicon is more or less quite balanced NC and NV, so you can say that this is about half of its band gap, and also you can say that this is minus half of band gap level. So these are material constants. So now remaining thing is EI. So we start from 3 different energy levels, EC, EV, and EF. However, EF was set to be 0, and EC and EV can be expressed as EI. And finally, we introduce such kind of expression. EI is related to the electrostatic potential by this simple rule, minus Q times electrostatic potential. Simply speaking, we define our electrostatic potential to point out our intrinsic Fermi level. That is the key way to unify all kinds of these different quantities. So if we adopt this kind of one, then the only remaining unknown variable becomes just electrostatic potential, because EC can be expressed as phi, and EV can be also expressed as this phi. So all kinds of unknown variables in our Gauss law shown here can be expressed. Yes, it is electrostatic potential itself, and also hole density can be expressed as the local electrostatic potential, and electron density also can be expressed as function of a local electrostatic potential. So when we apply this kind of argument, which is strictly valid only at equilibrium, so please note that that is valid at equilibrium under the Maxwell-Boltzmann expression approximation, then we can have a certain equation which has only phi as an unknown variable, and that is non-linear function or non-linear equation for our phi. So therefore, it is called the non-linear Poisson equation. So simply speaking, when I say the non-linear Poisson equation, it is nothing but Gauss law. However, not general Gauss law, the Gauss law, which is suitable for only at equilibrium cases. That is nonlinear Poisson equation. So now it is clear that if we wanted to analyze the device, semiconductor device at equilibrium, we must solve nonlinear Poisson equation. Once we solve this nonlinear Poisson equation, then we will get certain quantity called as electrostatic potential, and from this electrostatic potential we can recover, for example, EC and EV, and from these two quantities also we can recover electron density and hole density. That is the way we get the equilibrium state of our device. So of course this is just a brief sketch of what we are doing in this device simulator. Actual implementation is quite tedious. However, in this course, you don't have to implement the code, so you can just use it. So please just understand this code are doing that. This code is doing that kind of job. So our TA, Mr. Seung Jung, will send you the DB passes, so the specific path in our exercise workstation. So please have this one, and this is the all input file for simulating this equilibrium situation. So let me just explain its grammar, because there is no other place to get information about this code. So please have a look at it. So here in this case, we just define the device. We assume that we have already made a CGNS structure file. So please load CGNS file, pn.cgns. If you wanted to have load different files, of course you can have a different name. Then you will have the one. And now you have a DB path. So this is the path for your material properties, and without this correct DB path, your simulation cannot run properly. But it really depends on the simulation environment. That is really a path for your given installation. So our TA will distribute the correct DB path. So for example, when I just capture my screen, it has its own my own path, but if you just type it into your system, then it doesn't work, because there exists no such path. So you must have a correct one. And once after this line is over, now you have the loaded device structure, okay? And its name is it is named as a PN, and after that we just specify certain physical description, physical model for this device structure, PN junction. One thing which is mandatory, in many cases this property is used to specify physical models, and in many cases you can just omit this property. If you don't specify anything, then you don't have any specific model. That is general way. If you don't specify the mobility of your electrons and holes, it means that you will use just constant mobility for your electrons and holes. That is quite simple. However, there is one single exception. That single exception is shown here. You must specify this effective intrinsic density model. That is, and you must specify something, and here we are currently using no bandgap narrowing model. Bandgap narrowing, what is the bandgap narrowing model? If we have sufficiently high doping density, then actual effective energy bandgap is actually slightly reduced. If you have more and more impurity inside that system, then if you have quite clean and system, then previously EC and EV. However, if you introduce many dopants inside this system, for example, nearby EC, then you have a certain island which is not far away from this conduction band level. So although they do not contribute to the electron conduction directly, but once you have certain electron already occupying this state, then it is quite probable to later it jump into conduction band level and contribute to the electron density. Simply speaking, think about this one. Here we have a certain lever, and it's quite wide, and a person is here and wanted to jump there. Oh, it is quite wide, so it is very difficult. But instead of that, let's say that here nearby this the other side, we have a small stepstone here, although quite small, and not far away from this the other side ground, but anyway it is slightly closer to this guy. Then what will happen? It greatly help this guy to jump and jump. So simply speaking, although this one itself is not contributing to the electronic conduction, but it can be working as a stepping stone for our electrons, its journey to the conduction band. So if we have quite a high impurity density, effectively band gap is slightly narrowed. Also, maybe you can ask me this question: well, is it really important or not? So actually it doesn't matter. So it is important, especially if you have electrons and holes playing significant role inside your system. For example, if you are considering a unipolar device like MOSFET, then relatively it is less important. However, if you consider PN junction or bipolar junction transistor, this kind of effective band gap narrowing effect is critically important. Then why did you say no band gap narrowing? This is just a simple demonstration of our simulation capability. Later you may change this option to the other one. So anyway, after this job, now you have a correct device structure with minimal physical model. Of course, if you want, you can add more and more physical models into it, but it's just up to you. And here now you specify the nonlinear Poisson equation. So this one is specifying nonlinear Poisson equation. Then how can we find a nonlinear Poisson equation? There is nothing like a nonlinear Poisson equation. So equation type is just set as a Poisson, and if that is used standalone, then it is interpreted as its nonlinear form. So if we introduce other equations, accompanying equations like a continuity equation for electrons and holes, then it becomes its general form. But without them, it becomes its specific or specialized nonlinear form. After that, it was just declared declaring nonlinear Poisson equation, and now we solve it. If you eliminate this job, then just declare equation and do nothing. The actual solve happens when we have this solve routine, and which equation is solved, this EQ law is solved. For example, if I change this law name as just DC law, then keep this one, then that will make an error message, because there is no one like EQ law. So you must synchronize them. So if you say A, then there should be A. So it means that also you can define multiple laws within your code. You can define the law for equilibrium, law for DC simulation, law for transient simulation. Many different laws can be declared, and also you can selectively select one of them and apply it to your analysis. So just to say this one, then you will have the solution, and that solution is saved as this CGNS file called as pn_equilibrium.cgns. So your first exercise should be this one. Now I assume that you can visualize your pn.cgns, but when you just use this command file, then you will have pn_equilibrium.cgns. So please just try to visualize your electrostatic potential at equilibrium. This one shows the values of your electrostatic potential on the surface. Actually, this is volume, a cuboid, and every point inside this volume, we have a certain value of electrostatic potential. However, this volume view, three-dimensional view, just shows the surface value of our electrostatic potential. And we may have different options. For example, conline graph. Along a certain line, you can get the point-wise value. So I wanted to stress that that is typically very important for our analysis. So in the left side, we can see quite a beautiful three-dimensional view, but it is good for visualization, but it does not give us the exact number. So since we are talking about the performance improvement, we need to have the exact number. So in order to get the exact number, it is always good to have this cut line graph. So for details, please watch our already uploaded video in my YouTube channel. So how to draw a cut line graph, so you can do it. It is not that easy if you are a newcomer for this ParaView program. So it is not related with my program, G-Device, but it is the matter of familiarity to the ParaView. So ParaView has many functionalities, so you need to spend some time to get familiar with this one. So here you have electrostatic potential as a function of a position g, for example vertical position, and here you have n-type region, and here we have p-type region. So that's the reason why your electrostatic potential is quite negative, minus 0.4, and here you have quite a high value, quite positive value, quite close to almost 0.6. It means that your n-type doping density is much higher than the absolute value of your p-type doping density. So you have n plus p junction in this case. And where is the metallurgical junction? So this 1 micrometer is set as the metallurgical junction, the junction determined by doping density, and you can see that actual variation of our electrostatic potential only occurs in this p-type region. There is no potential changes in n-type region because this is just one-sided junction, n plus p junction. Although we have small differences here, but it is not visible at all. And now we have almost one-sided junction occurring nearby this p-type region, because p-type doping density is much lower. So in order to keep the charge balance, we must have a much wider depletion region compared with this n-type region. Very short distance of n-type region can be sufficient to match the charge balance. Okay, so up to now I have just shown you this electrostatic potential, but also we have different quantities. So for example, you can visualize also electron density and hole density. This is the given name for these two quantities, N and P. So why? It is because this is a quite much accepted convention in TCAD community. So representative tools are using this name. So I'm just following their conventions. So E density and H density, hole density, and you can also try to draw it. So please also try a semi-logarithmic curve for your densities. This one is corresponding to the hole density, and this is corresponding to the electron density, and of course this is corresponding to our you can say this is a donor density, and this is corresponding to our accept density. After that it goes down and also goes down, and here we have a depletion layer. So this is quite a simple textbook example, but important one is you should be able to draw these graphs by yourself to be able to analyze our structure. Although this is right now PN junction, but later you will consider MOSFET, so you should be able to draw by yourself. And up to now we have thought about equilibrium property. Yes, now we can have equilibrium property, but in order to make a performance optimization, first of all, you should be able to predict the performance. Then what is the performance? That is nothing but IV characteristics. Then how can you calculate this IV characteristics? You must apply certain voltage to your terminals and measure current as a function of voltage. That is required. This is excitation, and this is the result of your excitation. So so how can you do that? For that purpose, we must construct a circuit. Here we have a PN junction. However, with only this PN junction, we cannot apply a certain voltage. What we have to do is prepare a voltage source and connect their terminals with a line and with a line. Then if we change the electromotive force of this voltage source, so for example starting from 0 to 0.7 volt, then it will work as a simple diode. So for that purpose, what we have done up to now is simply related with this part. Our PN junction shown here, just showing this one just showing PN junction. So we must also attach a voltage source to it. So that is required for our IV simulation. So now we have to introduce another or two additional things. Why do we need two additional things? One is, first of all, we have to declare this voltage source. Without voltage source, we cannot connect them. So we must declare our voltage source. Here we have a type, and this type really determines what is this device. So let's just come back to our PN junction. Previously, the type was a device type. So it means that it has well-established meshes, and we must solve certain complicated partial differential equation. That is determined in this device type. However, if we go to more simple one called as lumped, and it is just specifying a resistor, a capacitor, an inductor, a voltage source, a current source. Such kind of relatively simple ones are categorized as a type lumped. And by specifying this line, you can have a voltage source that is corresponding to this one. And if we stop here, then our current situation is, yes, there are two objects called as PN and called as battery. However, they are just independent, and there is no relation between them. So we must provide connection between their nodes. However, is there any guarantee that we have this kind of connection? Actually, what happens if we say these two terminals are just connected to that one, or all of them are just connected to that one? So is it prohibited or not? So it's up to you. Of course, if you say this way, then your result will be meaningless, but anyway, you have freedom to set or describe your circuit connection. So now that is this circuit schematic is described by another type called as circuit, and here in this case you can just specify their connectivity. There is only one reserved one, which is global, called as ground. This is small g and d, that is always assumed as ground. This is a global ground. Yes, you must have it, and it is named as, in this case, G and D. It means that its node is connected to the G and D. Then now we have a PN, and it has a cathode and anode. Where is the cathode and where is the anode? This is cathode and this is anode, and it means that cathode is connected to the ground. Where is ground? Yes, cathode is connected to the ground. And another case, in this case, that is connected to a circuit node called as in here. And please have a look at these last two lines. Now we have a voltage source named as a battery, and it has two contacts called as 0 and 1. 0 is reserved for relatively lower contact, and 1 is reserved to relatively higher one. So now we have a connectivity between 0 and ground. Yes, 0 and ground, they are connected in this way, and 1 and in. So we have this connectivity. So after this specification, you can understand we are just drawing simple PN junction connected to the voltage source. So that is a way we can do. And now we must specify our equation which is suitable for our IV characteristics. You can ask me this question. Already we have assigned or made a law called as EQ law. That was quite successful to analyze our PN junction. But why do we need another physical equation? It is simply because when you have a look at our previous EQ law, it only contains Poisson equation, and it is in its quite specialized form of non-linear Poisson equation. It means that electron density and hole density are just functions of electrostatic potential, and implicitly it is assuming the equilibrium case. So since we are now talking about the beyond the equilibrium case, so non-equilibrium case, this equation is not valid for general case. We need additional one. So that's the reason why we must declare another specification for physical model. Here previously we just had Poisson equation, but now we have a lot more Poisson equation for our PN junction, and here we have two additional equations. These are named as E continuity, H continuity. Please guess what are they? E continuity is continuity equation for electrons, and H continuity is continuity equation for holes. So when we have a set of these three, then they are called as quite a famous drift diffusion model. And yes, we are now trying to solve drift diffusion model. And what are they? We have three additional one. They have their own purposes. One is contact. So now we have anode contact and cathode contact, and we must calculate anode current and cathode current. That is specified this contact equation. So without this one, we cannot calculate current. So please add this one. Please do not omit it. And also, in the case of our voltage source, what is the equation for voltage source? If you have voltage source, the central equation you have is V1 minus V0 equal to your electron motive force. That is the simple rule, and simple rule we must apply to our entire system. That is specified by this equation with a quite strange name. So actually I took quite a long time to set this name, but anyway, so this is just a specification for our voltage source. And finally, we have Kirchhoff's current law, KCL, is applied. Now you can understand, although looks quite strange, this specification is nothing but just circuit analysis based on modified nodal analysis. This is just nodal analysis for given circuit. However, each circuit elements are quite much exaggerated. So although this voltage source is quite conventional, but another one called as PN junction. It is quite much bigger than our conventional simple expression. Inside it, we have a cuboid, and it has many different nodes in it, and we must solve different physical rules, and so it is quite much detailed. But simply speaking, if we have a look at from more global sense, we are just trying to do the nodal analysis of a given circuit. But some of them are highly detailed in its physical description. That is simple way of our simulation. Then, yes, that's it. Then we must solve that one. But if you just solve this equation with a newly defined DC law, then you will have no output. So we must specify the output, the format of output file. So here we have a new statement called as a book, and using this event one, now we can print out the quantities of PN junctions, anode voltage and current, and PN junctions, cathode voltage and current, are printed where in this text file, CSV file. DC_IV.CSV file is the output file. So let me just say that I wanted to name out.csv. Then what will happen? So once after this execution is over, instead of DC_IV.csv, you will have a new file called as out.csv. Then you can just open it and have a look at the printed numbers to draw something. So now you can have a question about this specification. Here we have two different things, PN, and another one is voltage source battery. But I have not added the event related with battery things. Why? Because they are just duplicated. But in general sense, you can add this one, event thing equal to battery and contact equal to 0. Then you will have also additional fields related with the contact 0 voltage, contact 0 current of this voltage source. You can print what you wanted to do. Okay. So now you will have this DCIV.cs file, and how can you visualize it? Also for its visualization using Paraview program. So I have made another separated video clip. So please watch it, this one, because this is not related with volumetric information. This is related with the CSV file. We need different tricks to draw it. But anyway, you can visualize these two different quantities using the same Paraview program. Okay, then now this is the final stage of our input file. What we wanted to do is apply certain bias voltage to our PN junction and observe the terminal current. So, for example, I wanted to apply a node to 0.7 volt. Okay, since that is of my interest, I wanted to just say that please solve the situation where anode voltage equal to 0.7. But unfortunately, it's not directly possible. So we need to consider two different things. There is no way for us directly change this anode voltage. What we can change is only in this circuit. We cannot directly say that this voltage should be 0.7. So we cannot make it so. Then what we have to do is, instead of that, the electromotive force of this voltage source becomes 0.7 volt. Once we have this electromotive force of 0.7 volt, since this reference node 0 is connected to the ground, this voltage is always 0, and this is always 0. And since electromotive force is 0.7, then now this node becomes 0.7. And since they are also connected, finally, it becomes 0.7 volt. So simply speaking, we cannot directly jump into somewhere inside this circuit, but should change only value allowed the force to change. So in this case, we can change voltage, electromotive force of our voltage source. That is done here. So we wanted to solve this DC law. However, what we can do is just to set a goal to be satisfied. What is the goal? Voltage sources, its voltage should be 0.7. Right now, it is not 0.7. Initially, it was 0, but we try to make it 0.7. For that purpose, the simplest way is just to jump into 0.7 and try to solve this system. But unfortunately, in many cases, it fails. So what we do is, okay, directly jumping into 0.7 volt would be too dangerous, too risky. So instead of that, slightly jump into relatively small value and jump. So just to change slightly this electromotive force. That is done in this solver routine. How can you control this kind of jump steps? That is given as this one. So max step 0.01 means that at initial case we have 0.0 volt and final goal is 0.7 volt. And when we say max step is just 100ths, it means that we will just change 7 millivolt maximum. Okay, so the difference, the entire range is 0.7 volt, and the maximum step is just multiplying 0.01, this max step value. So we will have a 0.007 volt as a maximum allowed change of our electromotive force. So that is the one we do this kind of a calculation. So here I just say that we cannot abruptly change it. It means that the voltage value from 0 to its final value. So we must continuously change each value, so without taking too much risk, and eventually arrive at 0.7, the given goal. So it is the main procedure to take our simulation time. Why we have to wait? The reason why we have to wait is, although we are interested with 0.7 volt, but we must solve 0.007, also 0.014 of 21, something like that. Yes, that is the reason. Okay, so anyway, you will have two outputs. Two outputs means that one output is the DC IV.CSV. This is for IV characteristics. This is text file. You can open it in your text editor, also visualize it in a curve. And another one is also the final stages physical quantities are saved in DTCO2025. Why it is saved there? It is saved there because it specifies plot prefix as a DC. So that's the reason why you have a DC.CGNS. Instead of that, if you say that GGG, then you will have the output file called as GGG.CGNS. So now let me just show you the entire info file for simulating our equilibrium state and non-equilibrium state. First, we start from loading the structure, and also we define voltage source and circuit connectivity, and also specify the bandgap narrowing model for our PN junction. After that, we prepare two different equations. One equation is for equilibrium, and another equation for set of equations for DC IV characteristics. After that, just to specify the output format, and this solve is related with the equilibrium property, and the next solve is related with IV characteristics. So once you type without any mistakes and type enter, then you will have the answer. From my environment, it took about 10 seconds to have the solution, but you know, our exercise workstyle seems to be a little bit slower than mine, so I'm not quite sure, but anyway, that can be done within a minute, I hope. Then you will have DC IV.CSV file. Please try to draw IV characteristics from 0 to 7 volt. So already you have performed the simulation with your goal with 0.7 volt. You will have all information to draw this one. Then you will get this curve. So please try to draw it. And now you have your homework. So your homework is simply draw this IV characteristics. So this one is a forward one. Forward means that you have applied positive 0.7 volt to your anode. But please try to apply negative bias to your also anode voltage. So how can you do that? Actually, what you have to do is simply say, instead of this positive value for your battery voltage, please try on negative value for your goal value. One thing we have to be careful is you cannot do it once. I mean that always we must start from 0 volt. That is a starting point, given starting point. So if you wanted to have forward sweep and reverse sweep, then you have to make a copy of this info file, and one just goes in positive direction, and the other one goes this negative direction. And please perform both of forward sweep and reverse sweep and draw these two graphs. You will see the well-known rectifying behavior. If you have a positive voltage, it conducts. And if you apply negative voltage, and it does not conduct. You will see that quite simple behavior, but I think that that is enough exercise for you to prepare our next exercise. Okay, so I think that that's it for today's lecture. And do you have any question? Okay, so then if you don't, please do it. So I will ask our TA to give you the correct DB path as soon as possible. And thank you and see you this Wednesday. Bye.